Hello students, I just made a quick video for you to step you through part 3 of the guided review on mechanical energy, because I think there's some questions that we all have about work and how work can change the total mechanical energy of an object or a system. There were 3 equations that I provided for you, and what they do is help put into context the idea of work. Starting over here on the right, work, it happens because of a force being applied across a distance. So if there's something doing a push or pull, and that push or pull acts on an object through some sort of distance, then we're going to change the total mechanical energy of that object. We'll be doing work. Work is also defined as a change in mechanical energy. You can also write that how we did in our lecture notes on mechanical work. And in our notes, this was called the work energy theorem. We say if ME1 is some starting mechanical energy, if the object has some sort of mechanical energy, some amount of it, and we do work on it, what we end up with is a new mechanical energy, which I've labeled here mechanical energy 2. So here's where we start. We do work on it. So whatever work is adding on to our mechanical energy, if work is negative and we're taking mechanical energy away, then this would be a negative number. Adding a negative number means that ME2 would be less than ME1, which makes sense because our mechanical energy is going to decrease. So let's take a look at some of the solutions to part 3. So question number 1 was that a snowboarder with a mass of 70 kilograms enters a half pipe at a height of 12 meters, but he only reaches a height of 9 meters on the other side. How much negative work was done by friction and air resistance? So let's start over here on the left. What I did was I drew a little diagram, and this is one of the best ways we have of listing out what we know. And it's a really important step in all physics problems to make sure we understand what is even being asked. What is the situation that I'm being asked to model? So I drew my snowboarder here as a little dot. On this side, I labeled a height 1, H1, equals 12 meters, because that's where he starts out. I've labeled his mass as 70 kilograms. And then we go down this half pipe and we end up over here. I labeled that position 2, and I said H2, the height at position 2, is only 9 meters, because this snowboarder goes down and comes back up and only has 9 meters of height on the other side. So immediately we know that work is being done, because clearly the snowboarder has lost total mechanical energy. And we talked about this in class when we looked at swinging pendulums and why the pendulum only swings back up to a height slightly less than where it started from. It's because we're losing energy on every cycle, and it can't ever attain the same height. So this is the same principle. Snowboarder can't get to the same height on the other side unless he were to add energy to the system by pushing or some other form of adding energy. Okay, I have my diagram, and now it's time for me to analyze the situation. Well, in position 1 over here, I wrote down my gravitational potential energy equation, and I know to use the GPE equation because the snowboarder has height. The form of energy associated with height is the gravitational potential energy. So I wrote GPE equals mgh, and I put a little 1 here to show that I'm talking about position 1. That way I don't confuse myself. I'm keeping my solution organized. So 70 times 10 times 12, that's mgh, equals 8,400 joules. I'm not told that he has any velocity. We're assuming he starts from rest, so kinetic energy is 0, which means that the total mechanical energy of the snowboarder at position 1 is just 0, or excuse me, is 8,400 joules. It's just consisting of GPE. Okay, so I have my mechanical energy over here. Then I'm going to go to position number 2 because I have information there that lets me calculate his energy. And if this is the highest point that the snowboarder reaches, I know his velocity is 0 at this point. All of his available energy is in the form of GPE, gravitational potential energy. So he can't have any velocity. I'm just going to write my GPE equation again, this time with height number 2. 70 times 10 times 9 is 6,300 joules. Ke is 0 once again because we're at the top most point that he can reach. So he spent all of his energy on height on either side. So Ke is 0. And the mechanical energy at point 2 is 6,300 joules. Okay, so mechanical energy clearly was not constant. The mechanical energy changed. And the only way that total mechanical energy can change is if the energy left the object or the energy was put into the object. Because otherwise, I mean, we cannot create or destroy energy. That's the law of conservation of energy. So as a consequence, if our total energy amount changed, something must have happened to it. It must have left our object, or we must have gained some. In this case, we clearly lost energy. We started with 8,400 joules of total mechanical energy, and we ended with 6,300 joules of total mechanical energy. So what was lost? Well, we can set it up as an equation. Work equals the change in mechanical energy. I also wrote my work energy theorem that my final mechanical energy, the mechanical energy at position 2, equals whatever I started with, mechanical energy 1, plus the amount of work done. Well, I know what two of these things are. I know I ended up with 6,300 joules. I know I started with 8,400 joules. So let's plug it in. And also, quite intuitively, we end up with negative 2,100 joules of work done. That is the amount of energy that friction and air resistance transferred out of the snowboarder as the snowboarder went from one side of the half pipe to the other. Now, I stepped through that a little bit quickly, and if you want, you can pause the video, rewind it, or try and work out the problem yourself to see if you get the same answer. I'm going to scroll down to problem number 2. Okay, we have a similar problem where we're going to be talking about work and total mechanical energy. So let's take a look. Number 2, a car with a mass of 1,500 kilograms is traveling at 5 meters per second. The engine of the car provides a force of 8,000 newtons over a distance of 25 meters. And what we have is several steps, A, B, C, D, and E, that are going to step us through figuring some stuff out about this car. And part A says, how much energy does the car have at the beginning? Well, if I look at what I know, I just have a mass of 1,500 kilograms, a velocity of 5 meters per second. I'm not told anything about height, and it doesn't seem like this car is gaining height or losing any height, so I'm going to say that GPE, gravitational potential energy, is not relevant to this problem. The only energy that the car has right now is the energy of motion, because it's moving. So I'm going to write down my relationship for the energy of motion. Kinetic energy equals 1/2 times the mass times the velocity squared. I plug in what I know, 1/2 mv squared, and I get 18,750 joules. And because I made the statement that there's no GPE involved in this problem because there's no height, I'm going to say that this is the total mechanical energy of the object. Because mechanical energy, as we know, is GPE plus KE. It's the sum of all your mechanical energies. And if all we have is kinetic energy, then this is all we have. So this is the total energy available, 18,750 joules. Part B, how much work is done by the engine? Well, things we know about the engine. First thing I'm going to do is write my knowns. I know that it applies a force of 8,000 newtons, and the distance over which it applies that force is 25 meters. I have a relationship between force, applied distance, and work, or the amount of work done. And that is work equals force times distance. So it's fairly straightforward to just multiply 8,000 times 25 and get 200,000 joules. Now this is a lot of joules because we start off with 18,750. This engine is actually going to do a lot of work on the car. 200,000 joules of mechanical energy are going to get added to the car. Okay, how much energy does the car have now? Well, let's set up our work energy relationship. Whatever I started with, mechanical energy 1, plus the amount of work I did, that's the amount of change in mechanical energy, is going to be how much I have at the end, mechanical energy 2. So here's what I started with, 18,750 joules. That's all I had to begin with. I added 200,000 joules of energy from the engine, and if I add those two numbers together, I get 218,750 joules. This is the new total mechanical energy of the car. And where did it come from? It came from the engine. We didn't just magically create the energy, it was stored in the form of chemical energy in the fuel. So it did come from somewhere, but work was required to transfer that energy into the car and make sure it was in the form of mechanical energy that's useful to us. So the next question is D. How fast is the car traveling now? I'm writing down explicitly GPE equals 0 because no height change has occurred. That's nowhere in the problem. We're just cruising along. And that means that I get to spend all of this energy, 218,750 joules, on motion. I get to put all of it into kinetic energy. So if I do that, I can just set up my KE equation. Here's KE equals 1/2 mv squared. I plug in what I know. I plug in 218,750 for the KE. Equals 1/2 times 1500. This is the mass of the car. The mass hasn't changed. And I'm going to leave v squared as it is because I don't know what v is. It's an unknown. Well, 1/2 times 1500 is 750, so I know I'm going to have to divide out 750 on both sides to get v by itself. So 218,750 divided by 750 is 292, and that is v squared. And to undo the squared, I got to take the square root of both sides. So square root of v squared equals square root of 292, and I end up with v equals about 17.1 meters per second. Okay, so it's just a straightforward use of the KE equation. Solve for your unknown, which is v. Part E is a hypothetical. If all of its energy were converted to height, how high up could it climb? So now we're talking about height. And this part E is saying, well, if we took all of the energy we have, how much energy do we have? We have 218,750 joules of mechanical energy. And we spent all of that energy on height. The energy associated with height is GPE. How high up could it climb? So I'm actually just going to assume that I spent all this energy on GPE. My GPE is 218,750 joules. How much height can I buy with that much energy? Well, mgh is 1500 times 10 times h. I'm going to leave h as a variable because I don't know what it is yet. And we can multiply 1500 times 10, which gives you 15,000. Divide out 15,000 on both sides. So 218,750 divided by 15,000 is 14.6 meters. And this will give you the total amount of height that you could achieve if all of this mechanical energy was spent on height. Okay, so hopefully this helps us understand a few new things about the relationship between total mechanical energy and work.